All right. Hi, everyone, again. I was going to pick up today on the week 2 slides close to where we left off. So welcome back to another remote learning session for Math 273. As a quick reminder, last time we talked about introduction to simple linear regression, which is, again, like the bread and butter, sort of one of the most important models for this course and for predictive modeling in general. So today we're going to continue with our introduction to this. So picking up on an example where we left off last time, we talked about how we can model final exam scores of students using, say, their midterm scores. So for here, for example, we had midterm scores for students that ranged from 0 to 50 points, and we modeled their final exam scores, which were out of a possible 100 points. So again, even though the scales are not exactly the same, we can still use a simple linear regression model to explore the relationship between these two things. And using R, we obtained our corresponding regression model output. So there's a lot to be unpacked here. The number of data points in our data set was 31. Our response variable was the final exam score that's indicated here. This R squared value of 0.57 is indicating sort of the strength of the relationship, of the linear relationship between the two variables here, the midterm and final exam scores of the students. And in particular, we can interpret this R squared value as saying that approximately 57% of the variability in students' final exam scores is explained by their midterm scores. So that's how we interpret this R squared value here. And you can think if there was a perfect correspondence between the two values, if, say, a student getting a 20 on their midterm meant they always got a 20 on their final, or a 30 on their midterm, they always got a 30 on their final, then this R squared would be 1, representing that 100% of where they're falling, their final exam scores are falling, is determined by, or is explained by, their midterm scores, for example. And some other values that are in this output include our y-intercept estimate of 18.7 here, our regression estimate, our slope estimate of 1.49. This column is representing standard errors for each of those estimates respectively. So it's describing the uncertainty in that estimate, in our intercept or slope estimate here. And this t value is representing a t-test statistic, which is sort of a standardized estimate value. It indicates or describes the statistical significance of our estimates, just in terms of how different they are from 0 or not. So, for example, this midterm score, even though it's smaller in magnitude, based on our data, we're more confident that it's different than 0 because it has a larger t-test statistic value than the intercept being different from 0 because the t-test statistic value is smaller for the intercept. So to reiterate that again, this t-test statistic value is describing how far away, how many standard deviations away, essentially, we see this value being from 0. That's roughly what it's standing for here. So moving on from this example, we can talk more about how we can assess our model in terms of the necessary assumptions for simple linear regression. So a good way to do this is to use plots or graphs. One very important one is the scatter plot. So that's the plot with all the points, the data points, the circles on it. So this is usually a great place to start. It's great for exploring if there's a linear relationship in our data, so if a simple linear regression is even appropriate for this setting. Residual plots are important as well. They show the amount of error that we're typically getting in our predictions or our fitted values. So this is useful because the points nearly always don't fall exactly on our estimated regression line, and so there's corresponding errors or residuals with each data point. And there's certain assumptions about the linear regression model when we fit it that are made about these residuals implicitly. So we'll discuss some of those and how to check them. So first, looking at this residual by fitted plot. So this is the residual or error values on the y-axis, and the fitted values, the y-hats, the predicted values based on our regression equation on the x-axis. So one assumption to check is if the residuals or errors have constant variance. And so essentially what we're looking for in this residual by fitted plot is we want the data points, the circles here, to have even spread as we go from left to right along the horizontal axis. We want even spread around this center dotted line, which will always be at 0. So here we can see the amount of space or the range between the dots is fairly consistent as we go from left to right. There's no, say, funneling shape, which would be concerning if we saw something like that. So, for example, we just don't want an apparent pattern in the variance of these points. So, for example, if we had something that was like, if we had our center line here at 0, and then we had residuals that were like this, so pretty tight around the line to start, but then started to fan out sort of as the x values got bigger. So if we have this fanning motion, this is one of the most common ways in which this assumption is violated. That would be violating this constant variance assumption. This plot is a good example of how this constant variance assumption can be violated, because the variance is higher for the residuals here for a larger x value, for larger fitted values, than here for smaller x or fitted values. I guess maybe we could, like, since they're fitted values, they're actually the y-hats here, and then these e's on the y-axis are our residuals. So anyway, so this plot that I just drew is an example of when the constant variance assumption is not met, and this plot here seems more reasonable. Stuff's never going to be perfect in the real world, so this one here is reasonable. Okay. Another plot that we use to check assumptions for a regression model is a QQ plot. Although first, I guess we're going to look at this histogram. So both of these plots we're using to check normality of the residual. So here we're looking to see if the residuals follow this bell-shaped normal distribution. So looking at a histogram, what we're looking for is this bell shape roughly to sort of be exhibited in the errors. And so here, again, it's not perfect, but this is certainly very reasonable for real-world data. This histogram certainly seems to indicate that this normality assumption seems fine. And looking at the QQ plot, what we're looking for to check normality is that we want the circles on this plot, the data points here, to roughly fall on this dotted line through the origin. So again, not every point is going to fall exactly on the dotted line for real-world data, and that's okay as long as they're not straying too far. And here I would say Certainly none of these points are very far from the dotted line. So this indicates that the normality assumption appears to be met for this data set, for the residuals. And we'll look at a case where this is not necessarily appropriate. So let's look at an example where some of these assumptions are violated for a data set. So we're going to start by, if you're following along in R, which you don't have to be, but just if you wanted to replicate this example for yourself, we can install the stat2 data package, which has a lot of data built into it corresponding to our textbook. And so we install it using this install.packages command in R, and then we can load it, make it available in our R session by using this library function. So we are looking at a data set on voltage across time. Specifically, this is an example from a book. So I'm not going to read the example for you because I know you can see it on the slide. So, but we're looking at a capacitor, and essentially we have measurements describing voltage across time that were taken every 0.02 seconds. So we're going to model the voltage as our response and use time as our predictor variable. And so to do this, we're going to start, as we should with most every data set, by making a scatter plot. And specifically, again, if you're following along in R, to do this, we first load the data by using this data function. And so we do it in this way because the volts data is built into the stat2 data package. Other data sets will have to load in different ways, but because this is a data set from an R package, we can load it in this way using the data function. And then to create a scatter plot, we use the plot function here. So here we have a much cleaner, more refined relationship. Most things in real life will not be this sort of clean cut in how two variables correspond to each other. But this is an example where it's nicely happening. So certainly as time is increasing here, from when this capacitor was turned on, I think, the voltage seems to be decreasing. Noticeably, there's a little bit of a curve though, so it's not exactly a straight line. This is a little bit concerning if we're going to just go ahead and fit a regression model, a simple linear regression model, because it assumes a straight line, a linear relationship between the two variables. So that seems to be, this linearity assumption seems to be a little bit problematic here. But let's go ahead for demonstration purposes and fit a simple linear regression model in R anyways. So we regress voltage on time using this linear model LM function in R below. And then we print the model summary output using the sum or summary function from the JTools package. So if you're trying to rerun this code yourself, you can use this sum function. Also, another similar function that works is the, you can just use a different function that produces a similar output, but it's just actually summary around the same thing, around our volt fit object. So if you have trouble getting the sum function to work, because we need to load the JTools package in order to use it, you can also use this summary function because it's built into base R. It doesn't require loading any packages itself. And I like to use this sum function because it looks a little cleaner in the slide presentations here, actually, is all. So. Okay, so After using the summary function, we obtain our output here, our corresponding regression output, and we have these same values as before. N, our number of observations or data points in this data set, is 50. Tells us what our Y, our dependent variable, is voltage. Again, we have the R squared, and our regression estimates down here. So again, a lot of information to take in, but we'll walk through how to interpret some of these values. But first what we're going to do is write down our estimated regression equation, or our prediction equation, and then interpret the regression estimates, the intercept and slope. And it's very important to say the appropriate units as we do these interpretations. So looking back up here, if we are writing out our estimated regression equation here, we have that voltage is equal to 7.575 minus 7.555 times time where normally I would be writing this on a whiteboard, but I'm trying, hopefully this is large enough to be visible. I think it will be, where voltage is measured in volts and time in seconds. So notice how I'm saying the units as well. These are important to mention in context because time could be in minutes, hours, days. That relationship would be greatly altered if the units aren't specified specifically. So it's important to say these in many contexts and in general. So this is our estimated regression equation, or our prediction equation. How are the intercept and slope interpreted? So I'm just going to say these. I'm not going to type them out. But our intercept is of 7.575. So we say the expected voltage at 0 seconds is 7.575 volts. That's how we interpret the intercept term here. For the slope estimate, for the regression coefficient estimate, we interpret this as for every 1 second later in time, we expect the voltage to decrease by 7.555 volts on average. That's how we interpret the estimated slope here. And so this was just for this specific data set, those interpretations, but it could be tailored to many different contexts. And it's important to understand, this is one of the main takeaways from this course, is understanding how to interpret this output, this regression output that we get from software. Okay. So now that we looked at fitting the model, even though that linearity assumption seemed a little questionable, let's look at what our estimated regression equation looks like when we plot that on. So we again use this R code here to do so. And the blue line on this plot is representing our estimated regression line. So here's where we can see that curvature in the pattern of the points is somewhat problematic. We're sort of missing the mark a bit. In general, it's not too bad, but there's certainly we're not quite capturing the true relationship, it doesn't feel like, between these two variables, time and voltage here. So certainly, yeah, linearity seems not met here as an assumption. Looking more formally at some of the other model assumptions, we first look at a residual by fitted plot. And here's where some of that issue with linearity becomes more obvious. So, and this is the case because when I say obvious, I just mean it's more clear based on the plot than it was before. In that we would expect, if the assumptions are met, to have sort of a random scattering of points again around this center dotted line, but instead we have this very apparent pattern in the data. Probably apparent is a better word than obvious. So this apparent relationship in the data indicates that our assumptions are not met here for linearity. Additionally, one of the important assumptions of the regression model was independence of the residuals, and these residuals certainly seem to be related in that residuals closer in time here, or closer in the x-axis, are more similar in value. So that's violating another assumption of the independence of residuals here. So our regression model does not seem to be appropriate to fit in this setting. But looking again anyway, we continue by looking at the QQ plot here. So this actually doesn't look too bad. Most of the dots are still falling on the dotted line here. So our residuals in general seem to be still following a normal distribution approximately, but it's the other assumptions that are more problematic. So what can we do in these situations? We could just give up and say, forget this data, it's useless. But no, we can sort of wring it out and squeeze more use out of this data set before we give up on it. And in particular, one way we can do that is using transformations of the data. And so this might feel like cheating, but it's really not. We're still modeling this relationship that's existing there in the data. So here what we can do is use the log function, the logarithm function, to transform the voltage values across time. So we create this new variable in R using this code that's actually the log voltage instead. And I named it log voltage here using this R code, but you could have named this anything you wanted. What's important here is this log function. This had to be spelled in this manner. So let's take a look at a scatter plot between this now newly created log voltage and time. So this looks very linear, much better than the first setting. It certainly seems like if we put a line of best fit, if we fit something through this, it's going to fit much better than our previous relationship. So here it does seem linear, whereas before it was not as much. So let's go ahead and we can fit a linear regression model using this new log transformed data. And again, we can print the model output using the sum function from the JTools package. So we have to load the JTools package in order to use this. And looking at our regression output, we can see our R squared is significantly higher. We're now explaining 99.9% of our response values with this model. So nearly everything is explained in this model that we've put forth. So certainly seems like an improvement over the first approach without transforming the data. And notice that our estimates are very different this time. So this is mostly in part due to the fact that we're now working on the log scale for the data rather than the untransformed scale. So these estimates aren't interpreted in the same way. So we can write down our new prediction equation here again. So let's go ahead and do that. Okay. So now, instead of voltage, just plain old voltage, we have log voltage equals 2.190 minus 2.059 times time. And we specify the units again. Where voltage is measured in volts and time is in seconds. Okay. So this is our estimated regression equation, or our prediction equation here. Again, very different units than last time, and we'll see why that's important. So here, we can think about if we had a time of 1 second, what is our predicted voltage for that time? And so we have two different models here. We have the untransformed model and then the log transformed model. We can get predictions for both models, but they're not going to be the same. So let's see what we get for both of them. And then we'll keep in mind that we're wanting to get the predicted voltage, not the predicted log voltage. So we'll have to transform back after getting our prediction in order to compare the two approaches. So looking here for the log transformed model, if we plug in a time of 1, we should get that we have an estimated log voltage after doing some algebra. We should find that we have an estimated log voltage of 0.131, and that's log volts. So if we want to convert that just to regular volts, we need to use Euler's number set to the power of this value. So e to the power of 0.131, which undoes the log function. And here, if we get that, we end up with 1.14 volts. So that's our estimated volts. Is our predicted voltage for a time of 1 second. And Euler's number here is just a constant number that's about like 2.71. So it's the same as taking about 2.71 to the power of 0.131. So using a calculator, we could get that this is about 1.14 volts. Similarly, using the not log transformed model, if we go back all the way to our model output for this one, we can also get a predicted voltage, so 2.190, oops, that was the other model. So for this one, we have 7.575 minus 7.555 times 1 and then we should get that that is 0.02 volts. And we don't need to transform that because that is already on the voltage scale. It's not in log volts. So very different predicted value. And if we look at the scatter plot for this, for our predicted equation, we see down here for a time of 1 second, which is about here, it's actually off the plot. But if we imagine this blue line continuing, we see that we would get a very small estimated voltage. So that 0.02 is what we're going to be getting on this blue line if we extended it down to 1 on the x-axis here. And that's for our first model. For our second model, the log transformed model, again, we got a predicted value of 1.14 volts, so very different. And we can see that on the, sorry, I'm moving around a lot. On the plot here, I actually don't have the line of best fit on here, but if we put the line of best fit, which would be a blue line here, straight through the points, would look something like this as our estimated regression equation. We can see here at a time of 1, we get a log voltage, again, of about 0.131, and then we transform that back to get that final voltage estimate of 1.14. So these models give a different estimate, 2 different estimates for a predicted voltage at a given time. And that's okay. That doesn't mean anything's wrong, especially since the first model, the assumptions for a linear regression appeared to be violated. So that can sort of contribute to differences in 2 models fitting the same data like that. So looking at our log transformed model, which we're hoping adheres to the assumptions of linear regression better, we can now check the residual versus fitted plot and QQ plot to see if those are better. So first, checking with a residual by fitted plot. This still does not look great. There's still this pattern in the residuals when we really want this random scattering around the center dotted line. So still not great in terms of independence of the residuals, because we really want no apparent pattern in this residual by fitted plot. So this assumption does not appear to be met still. However, again, looking at the QQ plot, most of the points fall along this dotted line, so that seems okay still. This normality assumption appears fine. So we sort of still have normality being fine. The independence of the residuals is still a problem, but we improved upon the linear relationship in the data, because here now there's a very clearly linear trend in the data rather than that curve. So we gained one assumption being met. So it's still not perfect, but good enough to use. And so in the end, when we think about which prediction should we use between the 2, it's good to think about how the assumptions, more of the assumptions were met for the log transformed model than the not log transformed model. So in the end, we would want to go with that predicted value. And so that about wraps up for an introduction to some of the assessments of the simple linear regression model. Just to reiterate again why the log transformation might seem a little bit cheap or that it's not allowed, it's very helpful. Like in this case, it can give a better predicted value, which is more useful. But we do, some people argue there's a loss of interpretability because the predictions are on the log scale. Although if you convert back, arguably, that interpretability is still there. So There are pros and cons, a little bit of a loss of interpretability, but probably better predictions, better predicted values using transformations. All right, next class we will start continuing with regression, and Friday again will be the coding session. So I look forward to seeing you then.